these latitudes and longitudes. So, and the longitudes, they all meet at the North Pole and the South Pole. So you take any two of them and they intersect. They're not parallel at all. You might wonder if those are lines. But still, you have the horizontal lines, the latitudes, and they don't meet. They seem pretty parallel. The problem is they're not lines. I don't know if you ever thought about this, but lines, aren't they 2 points that you might have? You say, what's the shortest distance between them? A straight line. Right? So what's a straight line on Earth? Well, it's pretty easy, right? We've gone straight lines. You keep making straight lines. You keep going straight. And, well, you're not going to do this. You have to actually take some right turns, very imperceptible ones, to stay on one of these well, they call them parallels, but they're not. One of these latitudes. Turns out it's a little bit easier to see if you put the Earth there. So remember being on a plane and you pull out the magazine to see where are we flying, how are we getting there. So say you're going from San Francisco to Beijing or something, and you look at the map and you think, why don't we just go straight across the Pacific? It's got to be shorter. It goes up, way up around, hugs the coastline. You think, well, maybe that's a good idea because, you know, when we slam down from 20,000 feet at 600 miles an hour, you want to have some ambulances nearby for the survivors, right? It's a good idea. But it's not that. That's actually the shortest distance. You can see where LA and Seattle is and the coast here. And look at this. All the way to Seoul, Tokyo, around this area. It's pretty straight there. This is part of, if you continue this line all the way around, it would wrap around the Earth and come back. It's something that we call a great circle. It's like a equator. You know how the equator works? It cuts northern and southern hemisphere. It cuts the Earth in half, equal sizes, right? Any of the longitudes that you see here, right, do the same thing. They cut the Earth exactly in half. It's the biggest circle that you can make around here. It's a great circle. And those are the lines. If you want to go the shortest distance from one city to the next, you follow a great circle. And you might even have one. Where are the geeks again? See where you're? A globe where you can tilt the Earth and tilt the equator up. And so you can pick 2 points, any cities you want, and make that equator-like thing go right through them, and you'll know what's the shortest distance. And so, at least on this surface, do parallel lines exist? Of course not, right? So, in the words of Borat, these lines are not parallel. So, I mean, this is Euclid. This is 2,300 years ago, right? He lived 300 BCE. So we've been living with this lie for 2 millennia. It wasn't until Lobachevsky, a Russian mathematician, and also János Bolyai, who is Hungarian. Let's hear for the Hungarians. Around 1820-ish, discovered that the parallel lines is sort of, it's not a gimme. You get a choice. Sometimes you have it, sometimes you don't. They also discovered, so another way to put it is that put a line out here on a sheet of paper, draw it, and then pick any other point. Now ask yourself, how many lines go through that point that don't touch yours? And on the graph paper, it's just one, exactly one, right? But on the sphere, none, because every pair of lines intersects, right? Turns out there's another kind they call hyperbolic geometry in which you have many lines actually miss yours. Infinitely many. So you kind of have these options, 0, 1, and many, right? Original counting. And here's an example of one. This is drawn again by M.C. Escher, who learned about this geometry, I think, from Coxeter, who would have been 100 this year. And you see these white lines. These are fish. I don't know if you can make them out. It's all tiled together. It's a really nice pattern. But these white lines are the lines of the space. And if you want to, what's the shortest distance between 2 points, you have to go onto one of these lines. And how do you describe them? Well, they're curved, and they're actually circles that would continue if you could see the rest, but with a special property that they intersect at the boundary here. at a right angle. And that's how you make lines in this space. And just so you don't think this is a crazy idea and what a useless thing, right? It's absurd. It's not what we live in. Well, who knows? Here's one place it's definitely applied. So this is a reflection on a sphere, and the geometry of lines on this sphere, it's like an inverted sphere, is hyperbolic. And so you get actual example of these weird objects. Here's a tomato helicopter, which is a source of great study in recent years. So what I'm trying to do here is look at this red Earth and put a piece of paper, a plane on it, or a map, right? We all use maps. Let's say this green top here is a map, and we want to say, how good is this map? Does it approximate Earth very well? And, well, clearly not. It's like trying to wrap a soccer ball for a present, right? It's just a mess. And it's so bad that you see, maps of the world on the wall, and they're really distorted, aren't they? Right? Greenland is massive. It's bigger than Canada and the United States, but it's really not so big in reality, right? But your approximation of this round thing by a flat thing is terrible. And so it gets better, though, when you restrict just to a small little space, right? So here on the top, you've got a better approximation. Your map is smaller, and you can say, all right, well, if we go right here and left here, we won't get lost. I mean, it's interesting. If you look at, how in the plane you draw a triangle, and what do some of the angles add up to? Anna, I knew somebody who's currently taking geometry actually knows this. So 180, right? But if you draw a triangle on the sphere, its sum is bigger than 180. I don't know if you ever thought about this. In fact, a good example is start at the top, the North Pole, and just send two people out at 90-degree angles from each other, right? Until they reach the equator, right? So these are big people. And then when they get to the equator, have them walk towards each other. They did a 90-degree angle and then two more 90-degree angles. And that's a triangle on this surface. And its angles add up to 270. So you can get things that are way bigger than 180, all the way up to 540 degrees. I mean, so it's massive difference. So if you're trying to give somebody directions, take 4 left turns you'd usually need to get back to where you are. But on a sphere, maybe it's just 3 left turns, right? So you can't give somebody a map too big and hope that you're going to get them to your party where many hands make light work. Here the map is much smaller, and now the surface starts to look flatter and more closely approximate each other, right? So, I mean, maps work when you're only in Tempe. It's pretty flat, all right? So they work, but only locally. And this is a theme, a thread that I want to carry through a lot of what I'm going to say, is that we're approximating some kind of reality with a model and seeing how good is it, all right? And what can you say, and where do you get contradictions, and so on. So I just want to mention a few things about Euclid that they thought determined this sort of flat space that we may or may not live in. 2 points give you a unique line segment, and that's true on any of these 3 geometries we looked at. A line segment can be extended to just one line, not many, and that's true in all of these spaces. A line segment creates a unique circle by just fix one point and rotate it around. That's true. So far we haven't distinguished any of these 3 spaces yet. All right angles are congruent, meaning there's not several types of right angles. There's just one. All right? And that's Euclid's first 4 axioms.